Hi all, in this video I'm going to show you how Archimedes approximated pi. Now I was going to show you the way in which he calculated the values step by step using the methods of the time. However, the vid ended up being a bit too rambling and long, and even then in his work Measurement of a Circle, Proposition 3, in which he outlines the method, he leaves out a lot of the details like how he calculated the starting ratios, the cotangent and the cosecant values. You see that back then the Greeks, they did not think of the concept of trigonometric functions like we do today, and they did not work with the Indo-Arabic numeral system that we use today. Although they had worked out the ratio values for triangles with certain angles, and they were very adept with using them. So in this video I will show the gist of his method, but using a modern math notation and concepts. So what was the method? Well, in part 1 of Proposition 3, he begins by circumscribing a circle with a polygon. Now, Archimedes, he starts out with a hexagon, and circumscribing is just a fancy way of saying a shape drawn outside of another shape. He then proceeded to work out the successive polygons of higher number of sides to approximate the upper bound of pi. So I'll just draw this. So we have a circle with some radius and a line tangent to the outside of that circle. I'll just roughly guesstimate the center here. Now he starts off by creating an angle 1/3 of the 90-degree angle here. So that's around 30 degrees. That is 30 degrees. So, but I'm just guesstimating it here. So I think that's around 30 degrees. Now this is the half side of the hexagon. So now what he does, so we don't need all that. So what he does is he then bisects this angle again. So bisects is just halving that angle again. Then he halves it again. He halves it again. Then he halves it again. So he bisects the angle 4 times. And that creates a polygon with 96 sides, which is a pretty good approximation of the circumference of the circle. So likewise in the second part of the proposition, he does this by inscribing a polygon inside the circle. Again, inscribing is just another fancy way of saying he drew the shape inside of the circle without cutting outside of it. And again, he increases the number of sides by bisecting the angle 4 times, ending up with a polygon with 96 sides inside the circle. So again, I'll just quickly draw that. So we start off with a circle with some diameter. And what he does is he, again, 30 degrees. Like that. Then he bisects the angle again, and he does that 4 times to get the polygon of 96 sides inside the circle, and gives a pretty good approximation. So yeah, now as I said, the Greeks and he worked with ratios, not thinking on the modern concept of trig functions. He only started out using the cotangent and cosecant values for the 30 degrees triangle and bisected this 4 times, like I said. So in modern terms, he started out with, I'll go down here, he started out with cotangent 30 degrees, which is equal to the square root of 3. And that is just a ratio of a square root of 3 over 1. And Archimedes, in his work, he gives a value which is a bit less than this value of 265 over 153. So he starts off with this value, and that was calculated by him, and it was simply stating in the manuscript. And of course, this is the lower bound of the approximation of the square root. And because many of his works were lost, and we don't really know how he made such a good approximation. And he also started out with the cosecant value. Whoops. Cosecant of 30 degrees, or just call it theta. And we'll call this theta. And likewise, the starting degrees was just theta, which is it is 30 degrees, but that's just call it theta, and that is equal to 2 over 1 in that ratio. And he gives this as 306 over 153. Okay. Now, what he does with these starting ratios, he then bisects this, like I said, and he uses Euclid's Book 6, Proposition 3. In modern efficient formulation, we say that that's the cotangent of theta over 2, because he bisected the angle, which is equal to the cotangent of theta plus the cosecant of theta. Whoops. So he can use those previous calculated ratios to get the cotangent of the half angle, right? Now, from this, he uses the cosecant Pythagorean theorem from the Pythagorean cosecant formula, I should say. And this is cosecant squared theta over 2 is equal to 1 plus cotangent, squared over theta over 2. So using the previous value, the cotangent of the half angle squared, and all he did then was he got the square root of that, and he got his new values for the bisected angle. So yeah, so like I said, he did this, and so he used those calculated cotangent and cosecant values for the next iteration. So he bisected the angle again, and repeated using the two formula above for the new cotangent and cosecant ratio with the previous calculated values, which would approximate the circle circumference well with a small enough angle. So he did this iteratively. So from a 6 hexagon, he went to a 12 to 24-sided polygon, to 48-sided, and to finally 96-sided polygon that circumscribed and inscribed the circle, giving a good lower and upper bound of pi. So he finished with values of 3 over plus 10 over 71, which was the lower bound value of pi, and the upper bound value was 3 over 1/7. And this is quite a good approximation for that time. Now, let us do it in modern notation, and I'll just go to the next page here, and I'll start out with, again, the circle, and actually I won't need to put that in. Roughly put its center there. Now, for the inscribed circle, for the inscribed polygon, whoops, I'll just guesstimate this. Now, the vertex is that is equal to the radius of the circle, and the height of the triangle here is equal to something, and we'll just call it adjacent. And the base of the triangle is equal to the side of the side of the polygon. So the base there. Now I'll just quickly draw what would be circumscribed with the same, and I'll call this angle theta. Now for a circumscribed polygon, whoops, I'll just do it this way. Just a rough drawing here. Now here, the height of the triangle is equal to the radius of the circle, and we have the hypotenuse and the base again of the polygon for angle theta. Now let us do the inscribed triangle first. So we'll blow this out here. And I should mention theta for a polygon of n sides where the sides are all equal. Theta would be equal to 360 degrees over n. And of course, for this triangle, for the half of this base, so we have half over base. Now the adjacent here, and the radius is equal to the hypotenuse, and we have the opposite here. And of course we'll call this angle alpha, and of course alpha is just equal the half angle of theta. So half angle of theta, which is equal to I'll just write it in 180 degrees over n. Right, now with that we can calculate the half side of, well, the base or the opposite side of this triangle, and we can do that using sine. So the sine is opposite over hypotenuse, and here we have the opposite, which is 1/2 of the base, and I should put in sine alpha here, 1/2 of the base divided by the hypotenuse, which is r. So rearranging this equation, we get r sine alpha is equal to the 1/2 of the base. Now of course the base, or is this opposite side of the triangle, is just 1/2 of the side of the polygon, so we'll just times this equation by 2. So you've got 2r sine alpha is equal to the base. And of course, for the number of sides of that polygon, we'll get our circumference, or the perimeter of that polygon. So what we have here, we'll times this by n. So we'll have n times 2r sine alpha is equal to n. So this will give us the perimeter of the polygon, right? And this will be, because it's the inner the inner inscribed shape, this will give us the inner bounds of pi. So, well, I'll just call it the inner bounds of the circumference first. Okay. Now, for the circumscribed polygon, it's a little, I'll blow the triangle up here. Now here, the radius is equal to the height, so here we have r, which is the adjacent. The hypotenuse is equal to the vertex here, so hypotenuse, whoops, that's a funny looking y, and the opposite here, which is, of course, is equal to the half of the base of this circumscribed side, the circumscribed polygon with side. So here again, here we can use tan. So tan is equal to the opposite over the adjacent, which is equal to 1/2 of b over the adjacent, which is r. Again, rearranging the equation here, we get r tan alpha, I know I forgot the alpha here, but it's just alpha, is equal to 1/2 over b. And again, we times this by 2 to get the base of the side, or the side of the polygon, and we end up with 2r tan alpha. And of course, to get the total perimeter, we times that by n times. So n times 2r tan alpha is equal to nb, which is equal to the perimeter. So all in all, for the lower bound, we get n2r tan, the sine alpha less than the circumference. And here for the upper bound, we get n2r tan alpha. Alright, now of course pi is equal to the circumference over the diameter, right? But the diameter is just 2r, 2 times the radius of the circle. So what we get here, we get a final formula is n sine alpha is less than, so it's c divided by d, so pi over n tangent of alpha. Alright? So this is the formula we need to approximate pi. Now as n goes to infinity, we'll get more accurate values of pi, or the lower and upper bounds of pi. So using the lower bounds of, I'll use the lower bound for this, and we'll take n to equal 96 sides, the 96-sided polygon that is inscribed into the circle. So here we'll have 96 times sine, and we know as alpha is 180 over 96, so 180 over n, which is equal to 96. So what do we get here? Get my calculator out. 180 divided by 96 of that. So here we get a value of 3.141031951. Okay. Now, this value for n equals 96, even for the lower bound, will differ from Archimedes' value that he got of 310 over 71, because of course he used approximations of the ratio, the cotangent value, so it'll differ a little bit. But say we use, now we can go n equals to 100,000, right? Now I'll do that again. I'll type that into my calculator. And that gets us a value of 3.141592653 for all the numbers that the calculator can use. And so with using my Casio FX82MS, it's the second edition of this calculator type, this value is more than enough for calculations we might need in physics and engineering. So I hope you show. I hope you learned something, and if you found this vid helpful, please like and subscribe. Thanks.